Hello everyone. In this video, we are going to be looking at the quiz that I earlier on told you about. So we are beginning with question 1, which says, which of the following increases the rate of a chemical reaction? A is decreasing the surface area of reactants, increasing the temperature, removing the catalyst, decreasing the concentration of reactants. So think and tell me the answer. Think. So the answer is B. B is increasing the temperature. So increasing the temperature provides more kinetic energy to molecules, increasing the frequency and energy of collisions. This helps more molecules overcome the activation energy barrier, thereby increasing the reaction rate. Next, the unit of the rate of constant for a zero-order reaction is moles per liter second, liters per mole per second, C per second, then per mole per liter per second. Okay? What is the answer? We are talking about the unit rate, the unit of the rate constant for a zero-order reaction. We are talking about the units for K in that rate law. So what is it? The answer is A, which is moles per liter per second. And the explanation that we are looking at is that for a zero-order reaction, the rate constant K, the rate is equal to actually K because the concentration of the reactant here is raised to power 0. So this is equal to, rate is equal to K times the concentration of A to power 0. So it becomes K. So since the rate is expressed as moles per liter per second, the unit of K for zero-order reactions is also moles per liter per second. Next, a first-order reaction has a half-life of 10 minutes. How long will it take for the concentration to decrease 25%? Is it 10 minutes? Is it 20? Is it 15? Is it 30? Let's see. If we have the original amount, okay, decreasing to a half. So if it decreases to a half, we have 10 minutes that have elapsed. If the half decreases now to a quarter, so more 10 minutes have elapsed. So the total would be 20. That is for the case of a first order reaction. So the answer is B, 20 minutes. Because for the first order reaction, the half-life is a constant and takes one half life, that is 10 minutes, for the concentration to drop to 50%, and then another half-life to reach 25%, which is a quarter. So according to this reaction, equation that have simplified here, I'll just get from the original to a half of it, a half-life, from this to that, half-life. Then I add the two half-lives, each is 10, so I multiply by 2, giving me 20 minutes. A reaction is a second order with respect to A if the concentration of A is tripled, the rate of the reaction will increase by a factor of, so you have to remember the rate, of course, for the rate law for a second order reaction. So second order has rate equal to K times concentration of A squared. So if we triple A, then that means we are going to have 3 squared times concentration of A squared. So what will happen? Will it be 2? Will it be 3? Will it be 6? Will it be 9? An increase factor of the concentration, of the rate of reaction. So let's see. It's obviously 9, as I have already said, because for a second order reaction, the rate is directly proportional to concentration of the reactant squared, and that gives you 9 times faster. The rate constant of a reaction increases when the concentration of reactants increases, the activation energy increases, a catalyst is added, the pressure decreases. What do you think? What do you think? So the answer is C, when the catalyst is added. The catalyst lowers the activation energy of the reaction, allowing more molecules to react at a given temperature, and this increases the rate constant K. The slope of a straight line graph of natural logarithm of the concentration of A versus time represents A, the rate of reaction, the rate constant for a first order reaction, the half-life, the activation energy. What do you think is the answer? You can always pause and think. So the answer is B, the rate constant for a first order reaction. So the explanation is that for a first order reaction, the integrated rate law is natural logarithm of concentration of A is equal to negative KT plus the natural logarithm of the concentration of A at T, or time is equal to 0. This equation is a straight line with a slope negative K, where K is the rate constant. What is the order of reaction for the rate law? So here the rate is equal to K times the concentration of A times the concentration of B squared. So we said that the rate, the order of reaction would be sum of the order of this the order of the reaction with respect to A, and plus the order of reaction with respect to B. So this is raised to a power 1, this is raised to a power 2. So what is the answer? 0, first, second, third. What do you think? The answer is third order, because it is the sum of exponents of all concentrations in the rate law. Hence 1 plus 2 is equal to 3. Which is true for the activation energy? Which is true for the activation energy of a reaction? It increases when the reactant concentration increases, it decreases with the temperature, it remains unchanged by a catalyst, it decreases in the presence of a catalyst. What do you think is the answer? So activation energy, usually, if it is high, then it inhibits it slows down the rate. So if you reduce it, you have the rate of the reaction increase. So what do you think? So the answer is D. It decreases in the presence of a catalyst. So the activation energy is the minimum amount of energy required for a reactant molecules to collide and form products during a chemical reaction. It represents the energy barrier that must be overcome for a reaction to proceed. A catalyst provides an alternative pathway with a lower activation energy, making the reaction faster. For a zero-order reaction, the concentration of the reactant decreases. Is it linearly with time, exponentially with time, not at all, parabolically with time? For a zero-order reaction, the concentration of the reactant decreases. So let's see. So it decreases linearly with time. For zero-order reactions, we know that the concentration of the reactant is represented by this formula or equation. So is equal to the concentration of the reactant at time is equal to 0 minus K, which is the rate constant, times time. And this shows a linear relationship between the concentration of A and time, and it is telling you that this is going to be decreasing because it is a straight line with a negative gradient. In the Arrhenius equation, what does A represent? So this is a mistake. It is supposed to be A. So what is A representing? It represents the frequency factor, activation energy, rate constant, temperature. What do you think? The answer is A, the frequency factor, which is A. In the Arrhenius equation, K is equal to A times exponential of negative EA RT, whereby EA is the activation energy and A is the pre-exponential frequency factor representing the number of effective collisions. Ladies and gentlemen, thank you for enduring with us through this discussion. Remember to subscribe, share, like, comment, and enable us to serve you better. Thank you so much.